Hello, I'm Bob Brown, and today we're going to talk about subprogram calls and how data structures called stacks make subprogram calling easy. What is a subprogram anyway? Well, in high-level languages, you can write code that's variously called a method, a procedure, or a function. All of those are subprograms. No matter what we call them, subprograms add capabilities not built into a language. For example, most languages don't have a built-in cubroot function, so we might have to write our own. Usually a subprogram is called just by naming it, so we could write x is assigned cubroot of 27, and that would cause the subprogram cubroot to run, take the cubroot of 27, and assign the value back to x. The compiler or interpreter generates a call instruction to link to the subprogram and a return instruction to return back to the main program. Getting to a subprogram is no problem. The subprogram's name is a symbolic reference to the address of the subprogram. We just place that address in the program counter, just like a branch. We expect that the next instruction in sequence will run after the subprogram. So if I write x is assigned cubroot of 27, I expect that cubroot will run, store its value in x, and then the next thing that will happen is that print x will run. We have the same problem Hansel and Gretel had. Getting there is easy, but how to get back? We can't just store the return address in some memory location because it'll be overwritten if our subprogram calls another subprogram. In computer terms, a stack is a last-in, first-out data structure. Consider a stack of plates in a cupboard. The last one put in, that is put on top of the stack, is going to be the first one taken out. Stacks in computer programming work the same way. The last data item put onto the stack is the first one to come out. Computer instruction sets often have push instructions to put data onto the stack and pop instructions to remove it and place it someplace where it can be used. Stacks are usually implemented in main memory, or RAM, but some computer architectures have a hardware stack that's part of the CPU. It's possible for a stack to overflow, that is, to have no more room for data. That's like trying to put more plates than will fit into a cupboard. The stack structure is arranged to make stack overflow unlikely. Many computer systems load programs at the low address of an address space, but make the stack in memory grow downward from the highest address. In that way, any memory not occupied by the program itself is available for the stack. There's a popular website called stackoverflow.com. The name is a sort of joke on the bad things that can happen if a stack does overflow. So why do we need stacks? Well, subprograms need dynamic storage for return addresses. That is, there might be more than one return address, and we can't have a subsequent one overlay a previous one. Each subprogram must return to the address following the call or invocation of the subprogram. That last-in, first-out property of the stack provides a way to store return addresses in the way that they can be used to return to the proper location. Let's demonstrate that with a sample program and an animated video. Here is a piece of our main program. The part that's important for this video is the call to subprogram able. When able finishes, the instruction after the call, namely store result at location 1027, should be executed. Here's a look at able. Able calls another program, Baker. And here's Baker. When Baker finishes, it must return to able at the instruction after the call, namely store update at location 2050, and not back to the main program. Let's see how we can make that happen using a stack. We need to be able to watch the program counter and also the stack as we go through the animation. The main program calls subroutine able at location 1026. The program counter holds the address of the next instruction, so it contains 1027. The program counter value is pushed onto the stack. The address of Able, 2048, is loaded into the program counter, and on the next instruction cycle, Able begins running. When Able reaches the call Baker instruction, the program counter contains the address of the next instruction, 2050. The program counter is pushed onto the stack. The address of Baker, 4096, is loaded into the program counter. On the next instruction cycle, Baker begins running. When the return instruction in subprogram Baker is encountered, the top address on the stack is popped from the stack and loaded into the program counter. Items below the top of the stack move up. On the next instruction cycle, control returns to Able at the address immediately after the call to Baker. When the return instruction in subprogram Able is encountered, the top address on the stack is popped from the stack and loaded into the program counter. On the next instruction cycle, control returns to the main program at the address immediately after the call to Able. So, our two instructions, call and return, must work this way. A call instruction must push the program counter onto the top of the stack, then load the address of the destination subprogram into the program counter. A return instruction only needs to pop the stack and place the result in the program counter. We've solved the Hansel and Gretel problem. The use of a stack solves how to get back regardless of how many subprograms we call. That's not quite true. We have to be careful not to overflow the stack, but it would be unusual to get more than several entries deep. The stack can also be used to pass data to a subprogram, but we're not going to talk about that in this discussion.